from 8 to 9. So that is our usual class timing. And Saturday is actually, this Saturday is a Tuesday timetable. Okay. So that is why from 8 to 9 it will be 901. So Saturday is 8 January. 1. Let me write 8 to 8:50 p.m. So those who have, I have seen some of the students, almost around 10 students have not accessed their LMS portal. So do it by today, otherwise you'll be in trouble. You may not be attend the exam. So those who are not present, inform your friends. Okay, so let us continue where we have stopped in the last class. So we are discussing about the similar matrix. Two matrices are similar for A and B are said to be similar if there exist P inverse, invertible matrix P and P such that A equals to P inverse BP, and this transformation will be called similarity transformation, and this matrix is called similarity transformation matrix, is P matrix. Okay. Now we have seen that for a 2 by 2 system, it is not a very good approximation. For that, for 2 by 2 system, we have to solve a 4 by 4 system, 4 variable, 4 equations in order to get the P matrix. Now, this question will be whether we can get any more important information about the similar matrices without much difficulties. Okay. So there is a theorem. It says similar matrices have same characteristic equation and hence same characteristic values. For example, if you this theorem says if lambda is an eigenvalue of A, then this theorem says lambda is an eigenvalue of B also. Okay. Now the question is whether they are the eigenvector corresponding to this lambda with respect to A. If this matrix is X, then the eigenvector corresponding to this lambda for this matrix will be P inverse X. This theorem says. So let us just try to understand how this theorem can be proved. So since it is given lambda, assume lambda is an eigenvalue of A, then Ax equals to lambda x for some x non-zero vector. Okay. Then let us multiply P inverse A. So this will go as x. So assume P inverse P is an invertible matrix, because we are talking about similar matrices. So let A and B are similar matrices. Then what we can say, then this is our given information, then there exists E and P inverse such that P inverse AP equals to P. So this is our given information. When we talk about that A and B are similar matrices, then this relation will hold. Now we are assuming lambda is an eigenvalue of A. Our aim, is to show lambda is an eigenvalue of P. So that is our target. Now by the given assumption, because we are assuming lambda is an eigenvalue, so this relation will hold. And if we multiply, since this is lambda is an lambda is a constant, so it will come out, and let us write P inverse X. Okay. Now if you again multiply with, so let us write if P is an invertible matrix that we have given. Okay, so if you write here, let us write X equals to, substitute P inverse some Y, let us call Y. Okay, then it becomes P inverse A. In place of X, we are now substituting P times X equals to Py. If you write X equals to Py, okay, so this becomes Py, and then based from this relation we will get, since P is invertible, so Y becomes P inverse of X. So that is why we'll substitute now lambda times, here it is, in place of X we write P inverse. Okay, so this is a given already. So if you just substitute P times Y, so this will become identity matrix, and this will become By. Okay, so this is lambda Y. Now this indicates, this implies lambda is an eigenvalue of B.
Sir, but here eigenvector is different.
Yes, I'm telling this eigenvector is different. And the corresponding eigenvector is P inverse X. Because here Y equals to P inverse of P inverse into X. So this theorem says similar matrices will have same characteristic equation. It is not talking about characteristic vector. It is talking about if you just summarize, if A and
So
B
once you go to previous slide.
are similar matrices, just a minute, then the theorem says characteristic equation of A equals to characteristic equation of B. This will imply, okay, if this happens, then this will happen, which implies eigenvalues of A, because characteristic equation will give you the eigenvalues of A are equal to the eigenvalues of B. Okay, so this is the summary of this theorem. So this is for the first line. Now the second line says, if X is an eigenvector of A, then P inverse X will be eigenvector of the other similar matrix actually. So here we have seen it. P inverse X is an eigenvector. Here we have seen the eigenvector was X. So P inverse X is the eigenvector of the similar matrix. Okay. So that's what the theorem says. Somebody was asking some doubt regarding going back to this previous slide, right?
Okay, sir. Start.
Okay. See, whenever I write here in this, in this PPT or this slide, in this screen, whenever I write, I'm not able to see who is talking and who is typing on that. Okay, so that is why I may not call you by your name. So that is why don't feel bad if I say somebody. It is not visible. So every time I have to come back to my Google Meet screen. Okay. So next, how about that other way? If okay, if characteristic equation of A equal to the characteristic equation of B, can you say of B, then can we say A and B are similar matrices? Okay, the answer to this question, so this is the answer will be no, because we have seen earlier one example that if we take 1001 and 1101, they are not similar. But if you just try to find out their characteristic equation, what it will be? Characteristic equation lambda minus 1 whole square equals to 0. So here also characteristic equation will be lambda minus 1 whole square equals to 0. But these characteristic equations are same, but these matrices are not similar. So the converse statement do not does not hold for these similarity matrices. If they are similar, then only we can claim this one. But if these are characteristic equation are equal, then we cannot claim that they are similar. So this is one counter example. Here it is. So this remark says of this theorem. Now there is another remark which calls that if A is similar to B and B is similar to some other C, then A is similar to the C vector, C matrix. So that's a very easy calculation. You can just combine this. So that's one recall. You can utilize this. Now, why we are starting this similarity matrices? Because you remember we have studied the concept of diagonalizability when a matrix is called diagonalizable. So this diagonalizability can be studied in a different way also. So this way is by similarity matrix with respect to the concept of similarity matrix. Now, another definition for diagonalizability of a matrix. A matrix A is said to be diagonalizable if it is similar to a diagonal matrix. Now, when we say a similar to diagonal matrix, A and B are similar. This implies P inverse AP equals to B. Now, if this particular B matrix is a diagonal matrix, then we call A is diagonalizable. Okay, so this is the idea. Here, for any matrix, B was any matrix. When it becomes diagonal matrix, then we say that A is a diagonalizable matrix. Okay. So that is why similarity transformation is very important to find the diagonalizability of a matrix. Now, we have seen that finding the similarity matrix is not an easy task. So how to get this P inverse matrix? You remember, if you consider this P as the model matrix, then our task will be easy. This model matrix is definitely going to be invertible matrix, provided this particular matrix exists. If the model matrix do not exist, then we cannot claim. Then we have to follow the difficult path for finding the similarity matrices. So to answer this question, how about finding the P matrix, is one way is actually to find the model matrix. Okay, so if you try to set of model matrices, is a smaller set, and containing this, you can see that similarity matrices. Okay. Similarity matrices is a bigger set compared to the model matrices, set of model matrices. Okay. Now we'll actually recall this theorem that if we have a square matrix of order n, this is said to be diagonalizable if and only if it has n linearly independent eigenvectors. So that is another way that we have already seen. And the remark says if we have okay, so this is a repetition. So if we have distinct eigenvalues, for example, characteristic equation, if A is n by n order, characteristic equation has the form of lambda minus lambda 1, lambda minus lambda 2, and lambda minus lambda n equals to 0. Also, lambda 1 not equals to lambda 2, not equals to any other. All lambda are distinct. Then this says that the matrix is diagonalizable. because everyone has the multiplicity as 1. N factors are there, each have multiplicity 1. So we don't have to worry about it. When the eigenvectors are distinct, all the eigenvectors are distinct. Now difficulty comes when eigenvectors are repeated. So for that we have to check the number of eigenvectors, number of linearly independent eigenvectors. Okay, so you have to be careful about it. Okay. Now another beautiful result for similarity matrices. If you write A times A is similar to A itself. Okay. If this is a diagonal matrix, then A is diagonalizable. A is similar to a diagonal matrix. A is diagonalizable. If I write A is diagonalizable, then it means A equals to some P inverse, or you can write A equals to some will be there P D P inverse, or this is also writing as P inverse AP equals to D. D is a diagonal matrix. Now I mentioned somewhere that we are interested in diagonalizable matrices because they have some special properties. For example, a to the power m, if A is diagonalizable, okay, so let us continue again. There is an important call. Okay, so if A is diagonalizable, then it has a property of this. So the thing is, if we know this diagonal matrix, and if we know P and P inverse, we don't have to calculate A times, that means this matrix A square, A cube, and then A power 4, A to the power, for example, A to the power 100 or 1000, okay, or 10,000 or 1 lakh. We don't have to compute every time. We just have to compute this diagonal matrix, because for diagonal matrix we have seen that if it is diagonalizable, lambda 1, lambda 2, and lambda 3, if this is a diagonalizable, whatever the power you put here, you can directly just put here. So this is the beauty of diagonalizable matrices. So similarly, this is for diagonal matrix, but if the A is diagonalizable, you just have to calculate this matrix, these two matrices, and this is power only, just directly put the power. So that's it, you will get this matrix. So this is why we are interested in diagonalizable matrices. Okay, next, there is another property that if we have a polynomial in D, For example, d cube plus 3d plus some matrix I. D is the diagonal matrix. Okay. So if you talk about the polynomial, so if you write it q of d of this, then this will hold that q of d will be of this form. So you can directly just put it here. So with this notation, if A is diagonalizable matrix, then we have this relation. So this is satisfied. We already know it will satisfy. Similarly, q of A. So if we have a polynomial in A, okay, so we'll just substitute this q of D. So we'll discuss one example. Then this idea, this theorem will be clear to you. So if we have this problem, for example, a 3 by 3 matrix, okay, then what we have to find? First, we have to find the eigenvalues. So for that, let us try to find out. Okay, solution says A minus lambda I equals to 0. So the characteristic equation will be here 3 minus lambda 1 minus 1, then minus 2 1 minus lambda, and then this is 2. Similarly, 0 1 2 minus lambda, okay, so this is 2 actually. Okay. 2 minus lambda equals to 0. Now if you just expand this determinant, you will get lambda cube minus 6 lambda square plus 11 lambda minus 6 equals to 0, and lambda equals to 1 2 and 3. Then for lambda equals to 1, you get corresponding eigenvector x1. Okay, so x1 you will get. So in order to find out x1, what you have to do? You have to solve a minus 1 times I and sorry, this, or you can just write times x1 such that the right hand side is no, yeah, that's it, that's right, equals to 0 0 0. So this will give you minus 3 minus 1, this is 2, 1 minus 1, then minus 2, 1 minus 1 0, and then 2. So here also 0 1, 2 minus 1, this is 1. Okay, so if you solve this equations, x1 x2 and x3 becomes 0 0 and 0. So there you get x1 equals to 1 minus 1 and 1. So for lambda 2, you will get 2 and a minus 2y. If you do it, x2 0 0 0. So you will get x2 equals to, this is 1 0 1. For lambda 3, you will get 3 a minus 3 lambda, sorry, 3i times x3, then 0 0 0. This becomes x3 equals to 0 1 1. Okay. Now the task is to find out p. You can take x1 x2 and x3. So for this, the matrix will be 1 minus 1 1, then 1 0 1 0 1 1. Okay. How about P inverse? P inverse, just calculate minus 1 1, then 2 minus, sorry, 1 and minus 1, then minus 1 0 1. So this is what we have P inverse. Now we try to calculate P inverse AP. Okay, you just verify that minus 1 1 2 1 minus 1 and then minus 1 0 1. A matrix is given as, this is 3 1 minus 1 minus 2 1 2, then 0 1 2, and then you just write down the P matrix 1 1 0 minus 1 0 1 1 1 1. So if you multiply it, you are definitely going to get 1 0 0 0 2 0 0 0 3. I tell you to verify these results. Okay. So this is what happened. Now the problem says, okay, look at the problem. Try to find out that P inverse. But we have calculated some other P inverse AP. Okay. And then we have to find out B equals to, B is a matrix for which we have to calculate A square plus 5A plus 3I. Okay. So what we can do now is, let us write A square plus 5A, then plus 3I. So this is what it is given by B. B is a matrix, or you can call it B is a polynomial in A. Okay. So just recall A times, since A is diagonalizable, okay. So here this implies, since this is a 3 by 3 and eigenvalues are distinct, A is diagonalizable. We can say A is diagonalizable. Since A is diagonalizable, so it will satisfy the relation P D to the power M and P inverse. Also, Q of A polynomial in A, will be P times Q of D and P inverse. These two will be satisfied. Now, if you look at this matrix, so A, since this is a polynomial in A, so Q of A, so let us write Q of A will be of this form. So Q of D, so P times, P is here. So in place of QD, okay, so let me just write down. So this is a Q of A. So this is Q of A. So if you put in place of A, if you put D, so you will get, what is it? So from here, you get Q of D equals to D square plus 5D plus 3I. Thus, we have Q of A equals to P times Q of D. That means we have D square plus 5D plus 3I and then P inverse. So this is just a simple D square. So we just need to calculate because we have seen that D is, what is our D? So this is our D matrix. So if you put, so P times D square, D is of this form: 1 square 0 0 0, 2 square 0 0 0, 3 square, plus 5 times D, 1 0 0 0 0 0, sorry, 0 2 0 0 0 3, plus 3 times I, 1 0 0 0 0 0 1 0 0 0 1, and then P inverse. So if you just calculate these values, so you will get D square plus 3D plus, sorry, 5D plus 3I will be 1 0 0 0 4 0 0 0 9. Then 5 times, so 5 0 0 0 10 0 0 0 15 plus 3 0 0 0 3 0 0 0 3, and the resultant matrix becomes 9 0 0 0 17 0, and then 0 0 27. The next task is to multiply. So a square plus 3, so that is b equals to a square plus 5a plus 3I, which is nothing but, we'll write down the p matrix. P matrix is 1 1 0 minus 1 0 1, and then 1 1 1, and then this matrix will be there. So this is 9 0 0 0 17 0 0 0 27, and then P inverse. P inverse was minus 1 1, then 2 2 1 minus 1, then minus 1 0 1. Okay, if you just simplify it, you are going to get 25 8 minus 8, then minus 18 9 and 18, finally minus 2 8 and 19. So I would tell you to verify these results, verify the calculations. So that's how we use the similarity transformation to study the structure of the matrix, given matrix, whether it is diagonalizable. If it is diagonalizable, it will satisfy some beautiful properties, and then we can easily calculate the polynomial. So this is a QA actually. Okay, QA is actually of this form. So that is why we have mentioned that we will be interested in finding the matrices of which are diagonalizable matrix. Yeah, so that's it. So like we have mentioned the powers of a matrix by diagonalization. So this is nothing new, already we have discussed that it will satisfy this formula. And just to give you another example, so you can say this is example 2. A is given, try to find out. Okay, so this is the matrix, similar type of matrix. Hence find a to the power 4. So you will get this matrices, eigenvectors you have to find out. Then you try to find out the a to the power 4 matrix. Okay. Now I wanted to discuss this topic, but I will leave it today, as I will discuss this concept of orthogonal transformation. Of a matrix, orthogonal transformation of a matrix, we will discuss in the next week. So till now, if you have any doubt, you can ask me.